Okay, hi everyone. My name is Derek Davis from the University of Rhode Island. I'm excited to welcome you to the next in the series webinars detailing the fourth gravitational wave transient catalog. So today's webinar is going to be focusing on tests of general relativity with candidates from the catalog. So without further ado, I'd like to introduce Ofek Björnholtz from Bar-Ilan University, who will be hosting today's webinar.
Thank you, Derek. Thank you all for coming and welcome. Again, this is a webinar by the three collaborations on our three papers on tests of general relativity, which were all published or posted on the archive just last week and submitted to app.jl. So you can find them on our LIGO documents document center here or on archive. These papers also have links to the open data. All the data for the figures, analyses, everything is out. So you're welcome to look at it, play with it, contact us if you have any questions. This science is supposed to be public. Without further ado, I'll introduce also the next two webinars on April 9th and 16th, talking about population properties of merging compact binaries and on the cosmic expansion rate from gravitational wave propagation. With me today are the other speakers. There's a slight delay. Okay, so Jan from Potsdam, Sridevi from Calicut, and Sweta from Birmingham. And to answer your questions on the chat and afterwards, we have online 5 panelists, Apotin, Elise, Stas, Nami, for various specific test pipelines. And Nathan here is the VK Testing GR co-chair, head of the paper writing team, and basically catch all for any questions anyone else leaves unanswered. So we have these 3 papers, and these 3 papers test general relativity using gravitational waves. Gravitational waves are a uniquely well-adapted probe for strong gravity. We divide it often into regimes in the morphology of the signal here, this waveform, looking at the in spiral, the plunge and merger of 2 objects into a single final object. In all of our cases, this should be a curved black hole. Then finally, a ring down, looking at how this object rings down, emitting quasi-normal modes, as it should, finally ending into a vacuum stationary curved black hole. We also have tests for gravitational wave echoes, which might have been suggested to follow the prompt ring down later on. We divide our tests, of which we have 19 pipelines. Some of them have sub-pipelines. So these are grouped into 3 papers. We'll try to do this webinar kind of following along the lines of this division: overview, parameterized tests, and final tests of the remnant. Okay, so paper 1 has this overview table and summary, which gives both what all of the pipelines are, which paper and which section you can find each one of them, what we actually look for, and kind of a highlight of what is the main result, the best constraint we have, or the best improvement of constraint that we have on that aspect of general relativity relative to either previous gravitational wave transit catalog papers, or if these are new pipelines, kind of what is the new main result and the new thing that we learned performing this test on the data that we have. So for example, if we have a factor of 1.4, then this particular test has improved constraints by a factor of 1.4. We're narrowing down, in this case, parameterized tests. We typically expect general relativity to be recovered with a parameter is 0. So we're narrowing down and getting closer and closer to that value. Okay. The catalog itself has many more events than we actually use. The testing GR group has decided to focus on the most confident and strongest events. So that is quantified in 2 confidence parameters. One is that we want at least 2 interferometers to see the event simultaneously. For O4A, this basically means both LIGO detectors in Harvard and Livingston. And we want a false alarm rate less than 1 per 1,000 years. So we've narrowed it down to 42 new events from O4A, plus legacy events from previous runs, a total of 91 events. And paper 1 also gives in tables 2, 3, 4, and 5 the per observation run list of events. the main parameters that decide whether we run on it or not. So the overall signal-to-noise ratio, the list of interferometers in operation, and kind of the chirp mass, which basically tells us which regime we are in. For very high mass signals, we're going to be looking mostly at in-spiral. For high mass signals, we'll be looking mostly at ring down and merger. For low mass signals, we'll be looking at a long in-spiral. And you can see which test finds which event to pass its selection criteria. Not every test examines the same thing. For example, the remnant tests generally look at events in the ring down or later, while the parameter tests, we have some of them to look at the post-merger, pre-merger, or every other combination. Okay. For many of our pipelines, what we actually do is run a Bayesian inference between different models. The basic model of our waveforms will be completely GR from waveform families, which are generally either from the EOB family or the Phenom family. And many of these will have additions or modifications for various effects introduced from would-be non-general relativistic theories, so modify the GR. And these will modify the waveforms in various ways. We run Bayesian inference, so we kind of look at all these different options, compare them to the data in each case, find what the best parameters are, and calculate how constrained these parameters are to be near what you'd expect from the GR values. So the non-GR parameters are expected to be around 0. We also combine results from different events, either in a restricted method, that is taking the deviation parameter to be the same for all events examined, or a hierarchical method, which allows for more flexibility for the deviation parameters, representing that we expect deviations could be dependent on physical parameters intrinsic to the system, that is the masses and spins of the involved objects. Now we're just going to give a few highlights of some of the tests we performed before the other speakers give in-depth look into some specific pipelines. So the residual test, for example, looks at the data subtracting the GR waveform and looking for any correlated power in both detectors, indicating that there's some leftover, some residual that was not captured by the GR waveform. This could indicate some deviation of GR that's coherent. So we expect it to be physical, but not modeled by the GR model. And in this case, we find that the residual SNR is low enough to be consistent with noise for all the events examined. Other consistency tests appearing in paper 1 include in-spiral merger ring consistency, that is looking for consistency in the inferred parameters of the system, GR parameters, mass and spin, from the low frequency regime, so mostly in-spiral, and the high frequency regime, so merger and ring down. We expect consistency to be around 0, so consistency between the mass and spin before, from the early or late part, high frequency and low frequency, and we find generally that this is consistent. The tensorial vector and scalar polarization consistency test looks to see if the data is consistent with the polarization being pure tensorial. In this case as well, we see that every polarization combination, not including tensorial polarization, is strongly disfavored in its base factors, while those who include tensorial polarizations are very near 0, because basically we're just allowing more freedom, but the physics is captured. The data is modeled well with the tensor polarization. A line of sight acceleration, not strictly test of GR, but it does test kind of the environment in some way of the binary merger. A binary merger happening in isolation should not have acceleration throughout the merger. If, however, it does, it happens around, say, a supermassive black hole, you could expect an overall acceleration as the merging binary orbits around the supermassive black hole, which means we'd have a different redshift contribution from the early and late part of the signal. Again, comparing these can give us constraints on the overall acceleration of the binary, and we find from these two events that this is consistent with 0 acceleration. So we don't have any non-isolation effects detected. Echoes are covered entirely in paper 3, and we have 4 different pipelines examining possible echoes after the completion of the ring-down stage of the binary merger. The 2 waveform model echoes look for specific waveform models of Shor-Didiaka and Abedi, and binary and black hole perturbation theory. These both inspire template models, which we put in and analyze to see if they can explain the data better than the pure IMR models. In both cases, we find base factors generally negative or unsupportive. The 2 minimally modeled pipelines, Bayes-wave and coherent wave burst, again look for coherent signal between the 2 detectors after the main signal should have ended. And again, these are both consistent with lack of any echoes after the signal. So thus far, we find everything consistent with general relativity. And I think I'll now pass on to more specific looks into specific pipelines, starting with generation of gravitational waves and parameterized in spiral tests. Jan, on to you.
Yeah, thank you. So I will be discussing the parameterized in spiral tests. And just as a reminder, here in the top right corner, there's the morphology of the waveform. And the in spiral is the blue part here, so the low frequency early time piece of the waveform. Just below, there is a plot of the amplitude of the gravitational wave, and one can see that there's quite a bit of power in the in spiral. But what the detectors are actually most sensitive to is the phase of the gravitational waves, which you can see in the equation on the left, which can be approximated using the so-called post-Newtonian approximation as an expansion in the velocity v over the speed of light c. So it's basically a power expansion with some logarithm decorations. Now, the parameterized tests, what they do is they take this prediction of general relativity for the phase, and they introduce modifications, deviation parameters, by multiplying basically the GR prediction with the deviation parameter. We do so only in a non-spinning piece of the phase. That's more a choice for how we normalize the deviation parameter. So it doesn't mean that we are excluding spin from the investigation. And this is useful because otherwise one introduces correlations of the deviation with the spins, which is very hard to sample over. So that's the setup basically. Now, those deviations, those modifications have to be switched off after the in spiral. And how exactly this is done depends a bit on the method that is applied. And also, we do introduce deviations for terms which do not appear in the general relativity prediction. For instance, for so-called -1 pn term, which could correspond to dipole radiation. Now, if you want to compare this to the formula, you have to know that each post-Newtonian order corresponds to 2 pieces in the n expansion, or 2 powers in velocity. So -1 pn means n equal to -2 in that formula. And we also introduce a 0.5 pn coefficient, which would be n equal to 1 in the formula for the phase. Now, we do have 2 main methods to do this test. The first one is the so-called flexible theory-independent method, where the modification can be added to any non-precessing frequency domain waveform model. And in our papers, we use it together with an effective one-body waveform model. The transition to the post-in-spiral regime is just done by some tapering, and you can adjust the frequency, and we choose it to be the peak frequency of the 2-2 mode, which is the dominant mode of the gravitational wave, typically. The other method is a test infrastructure for general relativity, or TIGER. This method is built into the phenomenological waveform models in the sense that the waveform model itself has parameters where it imports the knowledge of the post-Newtonian approximation for the phase. And those parameters then can be directly modified and one can sample over them. Effectively, this means the corrections are introduced in the co-precessing frame, but precession is allowed in this test. The transition frequency to post and spiral, however, cannot be tuned because that's also fixed by how the waveform is constructed, and it's close to the so-called minimum energy circular orbit frequency. Similarly, there are parameters in the waveform model with which one can tune the merger and ring down, and based on that, one can also build a merger ring down test, which is reported in the paper, but we'll not discuss it in detail here. Now, once one has these methods, there are different ways to proceed. The traditional way is to do single parameter tests in the sense that one varies one of the post-Newtonian coefficients, but not all at once, but one keeps the others at the GR prediction. The reason is that otherwise one gets very broad posteriors and cannot infer any constraints, any bounds. So this is why this is done. We also have in the paper translations of the individual tests of the post-Newtonian coefficients to specific theories, more for illustrative purposes. However, there's a new method, so-called principal component analysis, where actually one can vary at the moment 6 parameters, 6 post-Newtonian coefficients at the same time, starting from the 1.5 PN coefficient. Then one does get very broad posteriors, but one can look at the full 6-dimensional parameter space and find linear combinations of the parameters, which have a very tight constraint. This is so-called principal component analysis, and then one can report constraints on those constraint directions in the 6-dimensional parameter space. So now let's go to the results. So this is for the single parameter tests. And we do combine the results from most events using the restricted method here. And in the plot, you see the 90% bounds for the posterior of the testing GR parameter on the y-axis on a logarithmic scale, and on the horizontal axis is the PN order. If you look at the top, so to say, goes from -1 PN to 3.5 PN. The blue and red dots, so to say, are our results. The filled ones from the current catalog, the unfilled ones from the last one. And one can see that the bounds overall improve, which is great, by something like 50% up to a factor of 6 or 7 even. The blue dots are from the phenomenological waveform model from Tiger, and the red ones from effective form body waveform model together with the FTI method. Not all of the bounds presented here are the best ones available for the post-Newtonian coefficients, in particular for the low PN order ones, like the -1 PN and the 0 PN. One does get better constraint from binary pulsars. Also, for the 0.5 PN, the best constraint is coming from GW170817, which is the binary neutron star event that was detected by the LIGO-Kagura collaboration. The reason is basically that the low PN coefficients can best be constrained at low frequencies at early times, and with binary pulsars and also with binary neutron stars through gravitational waves, one just gets better observations for these low PN coefficients. But so to say, the binary black hole observations have a clear advantage at the high PN orders and the high frequencies. Now on the next slide, we show, next slide, could you try to switch off? Like somehow the slide control doesn't work anymore somehow. Whoop. So I was at the, yeah, exactly, that one. Thank you. So here we show combined results with the more generic method, where the deviation parameter can vary across events. The previous result with the restricted method is still shown in the unfilled distribution for comparison, while the filled distribution is the more robust analysis. And you see the bounds are a bit broader. That's just because the analysis is a bit more generic, and this broadens up the posterior, but it's more realistic, so to say. More realistic assumptions are made. Still, overall, we find consistency with general relativity for both of the analysis pipelines. So the next test is the principal component analysis test. Just to remind you, this is where we vary 6 parameters at the same time, starting from 1.5 pn, and then do this principal component analysis on the 6-dimensional parameter space. And here we show the 3 best constrained directions. The other directions, so to say, are not well constrained and are not shown. And we had 2 events in 04, in the 4th observing run, that were analyzed. And again, you see that results are pretty consistent with general relativity, and also the bounds are pretty tight, considering it's a 6-dimensional analysis. Now on the next slide, so it works again. On next slide are the combined results from a principal component analysis, but here we only can do the restricted analysis at the moment, which is not so reliable, and we also see some tension here. Namely, when we combine 2 of the 04 events with 4 events from the previous observing runs, we see that several of the TVR parameters are offset from 0, which one could say is okay, it's not nice. But the 5th parameter is only consistent with TVR at the 98% quantile for the Tiger analysis. However, the problems go away when we exclude a single event, namely GW190814. So it's quite plausible that this is a statistical fluctuation in the data of that particular event. So overall, it's nothing to be concerned of, and the analysis is still consistent with general relativity. And this can happen if you observe a lot of events. All right. So to conclude, I mean, we find the inspiral overall is consistent with general relativity, and we do have some nice illustrative maps to specific theories in the paper, which you may want to check out. And with that, I'll hand over to Sridevi, who will report on the propagation test.
Thanks, Jan. Now let's discuss about the test of GW propagation, which you can also find in the paper 2 of the teacher application. So according to the theory of general relativity, the gravitational waves propagate with the speed of light, and their velocity is independent of both the frequency and the polarization. The test of GW polarization, the test of GW propagation, as the name suggests, is tries to constrain the deviations from GR as the gravitational wave propagates through the fabric of spacetime. Any such deviations considered will be accumulated over the distance through which the gravitational wave propagates, which means we will get the best constraints from the events which are very far from us. We were very excited at this point because the GWTC 4 catalog contains many events which are greater than 1 gigaparsec distance. Now, to justify the objectives of the test, we have made certain assumptions here. The first one is GR accurately models the generation of gravitational waves, or the deviations from GR during the generation are not observable, so that any deviations observed are entirely due to the propagation effects. This assumption is excellent in most of the cases. For example, for the case of a massive graviton, the Yukawa length scale derived from the posteriors of the mass of graviton is of the order of 10⁻11 times the maximum distance between the binaries. So basically, the distance between the binaries over the Yukawa length scale is a measure of the deviations from the Newtonian potential. So here, for our case, it is of the order of 10⁻⁻11. which will lead to a corrections in binary GR dynamics, which will be less than of the order of 10 raised to minus 22, which means it's a very valid assumption. The next assumption is that the gravitational wave signal is described sufficiently accurately by the two tensorial polarizations similar to GR. Next slide, please. Okay, here I'm presenting the first test on the GW propagation, which is called the modified dispersion relation. So as I told you earlier, GR predicts the gravitational wave travels with the speed of light, in which case the dispersion relation will be of the form E square equal to P square C square. But here I'm considering a modified dispersion relation where I'm adding a parameterized term over the general GR dispersion relation. What this means is that the different frequency component of the gravitational wave will travel with different velocity, which will lead to morphological changes in the gravitational wave. Such morphological changes can be attributed as a phase modification in the gravitational wave signal, which will be directly proportional to A alpha f raised to alpha minus 1. So here A alpha governs the strength of the violation and alpha controls the frequency dependence of violation. In this test, we have considered 43 events from GWTC3 and 40 events from O4A. We have excluded BNS and NSBH events because they have long duration signals which can significantly increase the computational cost. For here, we have considered 10 different values of alpha ranging from -3 to 4 in an interval of 0.5. We have excluded alpha equal to 2 because alpha equal to 2 doesn't lead to any dispersion. It only changes the overall speed of the gravitational wave. We also included alpha equal to 1 because the group velocity is equal to the speed of light with leading order, and hence we cannot constrain the parameter A alpha equal to 1. The other different values of alpha are motivated by different alternative theories of GR, as you can see in the slide. Mainly alpha equal to 0 corresponds to the massive graviton theory. In this case, here we are also considering the negative values of alpha, which can happen in a dark energy phase transition. Can you go to the next slide? Excellent. So here I'm showing you the NTR results from the GWTC4 catalog. I'm showing you that all the 10 violin plots of the A alpha parameters. Here the gray background shows the results from the GWTC3 catalog, and the blue lines are the results from the GWTC4 catalog. So as you can see, the GWTC4 results are more constraining and are more consistent with GR. But if you look at the negative values of alpha, specifically -3 and -2, we can see that the GR lies outside the 90% of credit level. This is actually due to a single event, GW231028, and when we further investigated on it using some GR injections, we have found that this is due to some prior effect which favors deviations from GR over GR. So we have, when we exclude this event from our result, we couldn't find any significant deviation from GR. In this test, we could also able to better constrain the upper limit on the graviton mass by a factor of 1.16 compared to the GWTC3 results. So now the current best limit on the graviton mass is 1.92 into 10 raised to minus 23 eV by C square. Can I go to the next slide? Yes. So here is the next test on the gravitational wave propagation, which is called the space-time symmetry breaking. So this test is motivated by the quantum theories of gravity, which predicts local Lorentz invariance violation and CPT violation, which can lead to anisotropic dispersion and birefringence. So what this means is that the two polarizations of the gravitational wave can travel at different speeds in vacuum. The effective field theory model or the standard model extension accounts for this fact, and in the Lagrangian contains all the Lorentz invariance violating term, and each term is characterized by a mass dimension d. The process that we are interested in here is the anisotropic birefringence, which is appearing at a leading order for d equal to 5. So this will introduce a frequency-dependent birefringent dispersion relation, which will change the frequency domain waveform, as you can see in the bottom left panel. So here the modified polarization are written in terms of the GR polarized components, which are modified by a deviation parameter beta. So beta equal to 0 corresponds to GR. So beta is directly proportional to the parameter K effective, which can be written in terms of 16 KLM coefficients in the spherical harmonics. So here in this test, we are using the IMR Phenom XPHM waveform similar to MDR test. So here first we will derive the posteriors of K effective assuming a uniform prior. Then we will use the singular value decomposition of the spherical harmonic matrix to obtain the individual 16 KLM posteriors. Next slide, please. Yes, thanks. So here I'm showing you the results from the SSP analysis. It's only from the O4A data alone. So as you can see, all the 16 KLM coefficients are peaking at 0, which is consistent with GR. The O4A data alone provide the better constraint when comparing with the GWTC3 result by a factor of 2. In the right end, I am giving you the 90% upper bound for the magnitude of all these 16 KLM coefficients. And these are, as you can see, that they are very close to 0, or at far most, they are close to 1, which means they are very consistent with GR. So as a conclusion, from both the test of GW propagation, we couldn't find any significant evidence for GR violation. But with the addition of more events, we could able to constrain the deviation by a factor of 2 or higher when compared to the GWTC3 results. With that, I would like to hand over to Shweta to discuss about the ring-down test.
You're muted.
Shweta, you're muted. We cannot hear you.
Sorry. Now I will present the results from the third paper in our GWTC4 test of GR series, specifically the ring down test performed on the first half of the fourth observing run. In this paper, the central big picture question we're asking is, after the two black holes merge, does the remnant behave exactly like what GR predicts? After merger, the remnant curved black hole sheds its perturbation through a set of quasi-normal modes, or QNMs, which are exponentially damped sinusoids. Each of this is characterized by a frequency FLMN and a damping time tau LMN. The key prediction of GR is that these frequencies and damping time spectrum are uniquely determined by just two numbers, the mass and the spin of the black hole. This is a consequence of GR obeying the No-Hair theorem. Black hole spectroscopy is a program of detecting multiple quasi-normal modes and checking whether they are mutually consistent with a single Kerr black hole. If they are, then it's a strong confirmation of GR. The waveform models for the ring down is given in the equation here. Each mode is labeled by L, M, and N index, and each of them contribute as a damped oscillation weighted by the spin-weighted spherical harmonic function. So here we report three complementary ring down analysis: pi ring, PSEOB-NR, and QNM filters. And I will briefly describe both the setup and the result of each. If I can have the next slide, please. Okay. First, let's talk about the pi ring setup. Pi ring performs Bayesian time domain analysis of the post-merger signal using three progressively more informative template families. The first is called the damped sinusoid, which is maximally agnostic. It has free frequencies, free damping times, and no assumptions are made about the underlying space-time at all. It simply assumes the signal is composed of multiple damped sinusoids and measures all of these parameters from the data. Second is the Kerr template. And here, the frequencies and the damping times are constrained to lie on the Kerr QNM spectrum, with the remnant mass and spin as its free parameter. Third is what we call as the Kerr post-merger. And here it folds in the information from GR more heavily and is the most sensitive model that is being used. The amplitudes and phases are calibrated on numerical relativity simulation and are time dependent, which is important for the early post-merger part, which allows it to capture nonlinearities, overtones, and transient effects. This also has higher modes included in it. The free parameters are the final mass, final spin, and this template is used when used for the parameterized test. It has two additional parameters which capture the deviation of frequency and damping time of the dominant mode. A crucial methodological point that is relevant for all of the ring down analysis is the start time of the ring down. We vary the analysis start time from near the signal peak through the late post merger. We do this because the stationary quasi-normal description is only valid once the space-time settles down sufficiently. Starting too early will introduce systematic bias, and starting too late, you will lose SNR. The start time variation done this way allows us to verify that the results stabilize as expected, and we can catch anomalies if there are any. So here we analyzed 22 for A events that pass the noise threshold of detectable ring downs. Can I have the next slide, please? Yeah. So in this slide, on the left, we have the base factor plots that show the evidence of higher modes relative to a single mode null hypothesis as a function of time for all three templates. So we see no statistically significant evidence for higher modes in any event for any template in all the start times that are after the peak. The base factor after the peak remains consistently below 1, which is the dashed line you see. GW230128 shows a slight shows a very slight preference for an additional 200 mode, but it is not significant enough to claim a higher mode detection. Also, the parameter estimation of remnant mass and spin for all of the templates are consistent with 90% credible. Are consistent to a 90% credible interval level to the full in-spiral merger ring down analysis for all of the events here. Now on the right side, you see the parameterized test. We use curve post-merger template here. So there's an additional fractional deviation of frequency F220 and damping time tau220 from the GR prediction. So when you hierarchically combine all O4A events, we get the purple contour. Both parameter deviations are consistent with GR to 90% credibility and contain 0,0 within the contour. Though there's a slight preference towards a positive shift for the damping time deviation. So now here it's worth noting that there was a systematic tendency that was found that the events with relatively low SNR tended to yield more samples with positive deviation in one of the deviation parameter, even though their posteriors in themselves were mostly uninformative. So the combined results are also reported for just the 11 events with log base factor that was greater than 8, and that's depicted here in the teal color. Next, we quantify the consistency of GR using GR quantiles, which are essentially a fraction of posterior enclosed by an isoprobability contours passing through the GR value. This tells us how deep into the tail of our posterior distribution does the GR value sit. Smaller the value, better the consistency. The 4D hierarchical GR quantile, combining both the mean and the standard deviation of the distribution of the deviation parameters, is denoted here by Q4D GR. The error bars here are obtained via bootstrapping. The thing to note over here is this value is pretty high, and further study needs to be done to clarify this. However, there is no overall significant evidence of any deviation from GR that we can claim. Can we go to the PSCOB slide? Thank you. Next, we have the PSCOB setup. So here, rather than analyzing only the post-merger signal, the analysis introduces a deviation parameter for the dominant mode frequency and damping time directly into a full in-spiral merger ring down template. Specifically here, they use PSCOB NR V5 PHM. So this gives us, this setup gives 3 advantages. One, there is no start time ambiguity, which is a persistent systematic concern for time domain analysis for ring down. Second, you get to use the full signal to noise ratio of the signal. And third, The in-spiral constrains the remnant. In-spiral constrains the remnant and spin dominantly, and this breaks the degeneracy between the remnant mass and the deviation parameters that would otherwise limit the sensitivity of the test. The analysis requires that we need to have an SNR greater than 8 for both the in-spiral and the post-in-spiral portion. And it constrains and it focuses on constraining the deviation parameter of the dominant 2-2 mode. Next slide, please. Thank you. For all the event analyzed, the 2D posteriors for the reconstructed 2-2 quasi-normal mode frequency and damping time, as well as the inferred mass and spin, are consistent at 90% credible interval with the IMR estimate. GW23-12-26 has an SNR of 33.7, and this one provides the tightest single event constraint. When we combine the events, the joint posterior, which is obtained by simply multiplying individual event posterior, gives us the following constraint, which you can see in the box. And the hierarchical one also gives a similar constraint. The thing to note here is both show that the frequency deviations are consistent with 0, but there's a positive shift in the damping time. The GR 0.0, sits slightly outside the 90% credible region of the joint posterior. Then below the box, you can see a table that compares the results with GWTC3. So we see that the GR quantiles have increased, meaning apparent consistency with the GR has decreased when the O4A events are added. The joint 2D quantile goes from 93.8 in GWTC3 to 98.6. The hierarchical 4D quantile also goes from 66 to around 85%. While this is not fully understood, we think this is a spurious deviation coming from a small catalog size or the finite catalog effect. Once again, there is no strong evidence for any violation of GR with this, even with this observation. Can I have the next slide? Yeah. The third and the last test that we have is the QNM rational filter. This setup applies a frequency domain filter that eliminates specific complex QNMs from the ring down signal, and then compares the leftover residue to color Gaussian noise. Now, because the filter absorbs the mode amplitude analytically, the likelihood will always remain two-dimensional in a remnant mass and in remnant spin, regardless of how many modes are included. And this is one of the key advantages that this method has. The analysis uses a combination of two quantities to identify the presence of the secondary mode. The first is the detection statistics, which here is given by the curly T, that quantifies how much of the data supports the hypothesis that the data has one mode over the alternative hypothesis that it has more than one mode, specifically two modes. It also uses a joint posterior quantile for the remnant mass and spin inferred from IMR analysis, which is given as PIMR in the second box that you can see. The detection statistics exceeding the threshold level of 1% false alarm probability and simultaneously having a low value of PIMR is used as a way to support for the presence of a secondary mode. So this was applied on the two highest NR signals in for ring down, GW23 10 28 and GW23 12 26. For GW23 12 26, there was no compelling evidence of subdominant mode. But for GW23 23 10 28, the picture becomes a little bit more interesting. The analysis start time that is smaller than 2 TMF, which you can see on the rightmost plot. The detection statistics for 2-1 mode exceeds 1% false alarm threshold and improves the IMR consistency metric compared to the other candidates. So one thing we want to be very careful is about how to interpret this. We do not claim a confident detection of 2 to one overtone in GW23 1028, but the detection criteria for the QNM filter setup favors the data containing the overtone at very early times. The important caveat here is that this early on, the start time is this early on. When you have this early on start time, the stationary assumption of QNMs are the least trustworthy in this domain. And this will get contaminated by effects such as the transient effect, nonlinearity, and time-varying amplitudes coming from other artifacts. And these are not accounted for when we use QNM superposition model. So this needs to be considered more carefully. Thank you. With that, I conclude.
Thank you to all the speakers. Now we're going to go for the panelists and open questions from the audience. Derek, do you want to moderate, or should I?
Please go ahead. I think you can pick questions out from the chat list.
Okay. Okay, I've got the chat box open. But no questions yet. I also don't see hands up from participants. If anyone wants to, any of the attendees want to raise their hands or open a question or ask a question. If not, I can ask the panelists to say things that they want about their pipelines, especially pipelines which has not received much attention. Stas, would you like to say anything? Nami, Apratim?
So it looks like we are getting some questions in. So there's a question from Peter Shish, I'm definitely the name, about other results from cosmology. I think we can answer this one live. So Sridevi, Stas, would you like to discuss this? I think this is most important for the propagation test, because all the tests do have some trends on the cosmology.
Sure, I can try. Yes, so in principle, we have used a particular cosmology based on Planck, Planck 15, as far as I remember. And actually, there was a test performed on some events for propagation by varying the cosmology, and we did not see big effect by changing cosmology between, within reasonable cosmological models like Planck 15, Planck 18, etc. So there was not much dependence. We did not see dependence on particular cosmology, but of course we did not check something quite peculiar cosmological models.
Thanks, Stas. So there's also a question, which I think is alive, about an event that is not covered in this paper, so S2511 12CM. So I think this is not something we can discuss here. We should wait for the collaboration to come out with the final results here. This is not an OFOI event, so we will not discuss it.
Okay. Mark asks in the chat about the false alarm rate, if it's less or more than 1 per 1,000 years. So the false alarm rate is lower than 1 per 1,000 years, which means the expected time to get a false alarm is greater than 1,000 years in the denominator.
So there's also a question for an anonymous attendee about whether checking for quantum gravity or non-linearity of GR. So maybe I will answer this one as well, and whether you can comment if they would like. So we're not specifically checking for quantum gravity effects, but there was obviously some things like echoes which could come from quantum gravity, or just in general you have some deviation from GR. The nonlinear GR is all completely baked into our GR models. Modulo things are looking at just linear perturbations around curved, even though the curved background is a nonlinear solution of GR. So we are testing nonlinear GR and looking for possible deviations from it. The question about the PCA parameters. So, Elise or Jan, would you like to answer this?
Yeah, so the question is how the PCA parameters are normalized. So the normalization to start with is the one from the original test, the FTI and TIGET test, which means they are usually normalized to the general relativity prediction, and so they measure a relative deviation from them. Since PCA only includes coefficients starting from 1.5 pn, that's exactly how they are normalized to the non-spinning part of the general relativity prediction. However, then of course one takes linear combinations of those. But yeah, the normalization is the general relativity prediction. So one is what the GR coefficient gives, and yeah, I hope that answers the question.
Thanks, Jan. I think that does, and people can ask more if they need more information. So there's two actually related questions, one from Mark, graviton constraint compared with previous estimates, and also from Holly asking about how constraint compares. So I guess maybe Sridevi, can you discuss how these graviton constraints compare with the solar system constraints, and then maybe Jan, you can discuss some of the illustrative translations. Or at least if you would.
Yeah, so there is an estimated bound on the mass of graviton by this planetary ephemerides. So from their results, the upper limit is 1.01 into 10 raised to minus 24 eV by c squared, which is better than of an order of 1 compared to our results. But they're using some different method like the binary effusion, and we are using some other methods. So I think they are complementary.
Can Jan or at least would you like to please discuss the illustrative constraints?
Do you want to go, Elisa? Or?
Yeah, we can have Elisa.
Yeah, sure. So typically the constraints that we get from mapping these agnostic PN bounds to a specific theory are not as tight as what you would get from a theory-specific test. Usually like the same order of magnitude, so maybe like a factor of few less tight. Sometimes there's also tighter bounds on a theory from some different kind of test that doesn't use the gravitational wave signal in the same way as is done here. So yeah, there's a table in the paper that compares the bounds that we get to existing bounds, if you want to have a more quantitative answer.
Thank you, Elisa. Thank you, Jorge, for asking. Any more questions? Nami, would you like to comment on how the echoes relate to possible quantum gravity?
Yes, so in the echoes, we assume that the major ring down signal is reflected at the potential surface of the exotic compact object, but we can also consider about the quantum effect. So in the quantum gravity, so black holes can absorb only discretized frequency. So in the case of quantum black holes, we might see echoes. Yeah, but in our analysis, we didn't find any evidence of echoes.
Thanks, Naomi. So we have another question about propagation. So, Sridevi, you want to take this one?
So about the so I don't think we are considering any matter through which the gravitational wave propagates. We are considering the gravitational wave propagates through vacuum, and I don't think there is any criteria for the minimum distance. We are very interested in the events which are very far from us. I think there is no specific cutoff, but greater than a few, but greater than 1 gigaparsec is a better, as a very good distance that we can think of.
Yes, thanks. Just for clarity, these are the luminosity distances, because of course there are different distances in cosmology, and of course we do include the contributions to the matter to the cosmology we use, but besides that, there's no assumptions about matter between us source, because of course gravitational waves are very weakly coupled to matter, so we can assume for anything that's reasonably out there, it's absolutely no effect on the propagation. So maybe start or to discuss the graviton mass versus tension Hubble constant.
Frankly, I have no clue. I really don't know. I mean, we never thought about this. I mean, basically, we're just trying to see a really propagation effect, but we did not try to relate it to any tension in Hubble constant. Maybe if other people have better answers, sorry, I don't know.
So some people do have better answers, and those are the people who will be giving the Cosmology and Hubble paper webinar on the 16th of April.
Yeah, I guess for clarity, they do consider propagation effect, but not dispersion, but they may also have better ideas about how concentrated the graviton mass can relate to cosmology. So I guess we're at the hour, and I think we've finished the questions, so maybe we should wrap things up.
Last chance, anyone? Okay, thank you all for the participants, the speakers, the panelists, Derek and Casey for the administration and hosting, and everyone who came and everyone who asked questions. Read the papers, talk to us, come to the next webinars. Good luck.